So now, I guess we can start. Now, any questions before we start? Come again?
Can you run through that?
That problem? After everything is done, later on, not now. Okay. So we want to make sure that we get started with the machine learning exercise, and should be a good experience for you. I don't know how many of you know how to do coding. All right, a fair number. All right, so you can see there'll be good applications. All right, so you can see that there's going to be a fair amount of value added. So I think it's good. So Alison, the floor is yours.
Thank you. All right, thanks everybody for having me here, and my colleague Heidi. So just mention really quickly, the libraries, we have resources and support for data visualization. So if you ever have to do any data cleaning, getting your data ready, making charts and graphs, that kind of thing, we're always available to do consultations and to help. Various types of software from SAS, R, Tableau, Excel. So if you ever have any, you're doing your projects or you're doing your works and you want to meet and talk with a librarian to kind of, get some help or whatever, you can come to our main website or this website, which is our visualization specific website, and you can email us by clicking this link. And there's a whole, I'm up here on the top left, I'm Allison. There's a whole list of us here who can help as well. So just to know that you have us as a resource. We also have a lot of workshops. We have Tableau, R, lots of other GIS mapping types of workshops. If you're ever doing any kind of work and you're interested, feel free to check out our website. And my colleague Heidi is a collections and research librarian for engineering and data science. So we both like to use R, and we're going to be working a little bit with R today, which is a statistical computing language. And we'll get a little practice doing some machine learning with R. So I'll talk a little bit about machine learning and kind of why it might be useful in business and in finance. And before I do that, I just want to make sure everybody has the right software and the right files for the hands-on part of the workshop. And so this is the link that you'll need to go to download all the files. And I've already kind of showed you, if you were here a little bit earlier, I showed you kind of how to get access to the link. Make sure you're signed into your NCSU Gmail account. And then when you get to this Google Drive folder, just click on that link where the title of the folder is there. Click on that drop down and then go ahead and just download everything. And make sure you have the whole folder of files on your computer. And when you've downloaded it, make sure to go into your folder and extract your files. On a Mac, it's really easy. Just double click that folder and it will automatically extract everything. In Windows, you have to click into the folder, and it depends on what version of Windows you have, but often there's a little button that says extract that's in your view, and you can click on that and it will extract your files there. So just kind of pay attention to where your folder is downloading, because we're going to need to access it in RStudio. In order to do the hands-on part, you'll need RStudio and R installed on your computer. And Heidi is here to help if you had any installation issues or still need help with installing. Hopefully you were able to install both R and RStudio. R is like the code. RStudio is like the environment that's like the graphical environment that makes it a little bit easier to use R. But pretty much a lot of people who use RStudio because it helps with kind of file navigation and keeping things in the same project directory. So go ahead, if you will, open up RStudio. And you should see a kind of view that looks a bit like this. You're going to have 3 or 4 windows, depending on if you've ever used it before. And the thing that you want to pay attention to once you get RStudio open is your bottom right-hand area where you have a list of files. We're going to kind of go ahead and get this set up going right now. And we have to do some installing actually still. I know, I'm sorry, there's a lot of installation. Do a little installing, and then once you start that process, then I'll do some talking. And then when I'm done talking, it'll all be set up for you. So these files, this file tree is all the files on your computer. And you should probably see your home view. You'll see like documents folder, downloads folder, various folders like that. You want to find the folder of, it's called the ML class files that you downloaded from the Google Drive. And the easiest way to do that is to actually click on a little tiny button that has 3 dots on the far right side over here. Let me see if I can move it a little bit closer to the view. You see where I'm like hovering over this little area on the far right? If you click on that, it will bring up your files directory, and you can find your files that way. It works on Windows and on Mac. And then once you do that, you want to click into your directory. So see how I have a list of files here? You want to get to the point where you see those files there. Today we're going to be using linear.r, and we're going to be using our full underscore dataset.csv. Those are the two main files that you're going to need to have access to. So if, as you're doing that, if anybody has any issues that come up, please just raise your hand and Heidi will come by and help. Go ahead and open up linear.r by clicking on it. And when you click on a script file, this is what this is. It's a script file. It's just like a file of code. And the green stuff are comments that I've like written in to kind of help you understand where we are in the code and what's happening. The first thing we're going to do is we're going to set our working directory. So we're going to tell R what directory we're working out of, which makes it a lot easier to find the files we'll need later. So go ahead and click on, once you've got this opened up, you can go ahead and click on More. And More is on the lower right side. It's a little kind of like in the navigation area. There's a blue gear. Click on that and select Set as Working Directory from the dropdown. And when you click on Set as Working Directory, what you'll see pop up in your console is a little line of code. And that tells R that you want to be working in this folder. You could have actually just typed this and hit Enter, and it would have done the same thing. So you can type the code and set your working directory, or you can just do it from the drop-down menu. Either way. So I'll pull up where that is just one more time, so that you'll see if you're still doing this, that you'll set your working directory from that More drop-down. So every time you use R, you're going to want to do this at the beginning. Like if you use R in the future, you'll always want to set your project directory at the beginning, your working directory. Okay.
Can you please go back to the last step?
Yeah. So what we did was we found, have you found your file folder? Yeah, you found that, and you're in it, and then you want to go to More and set your working directory and click that, and it will pop up here. Have you gotten to that part? Was that the part that you were? Yeah. Okay. All right. And so once you have that done, we're going to move to step 2. This is the part that takes a little while. So R is like, so I would quickly say something about R. It was created in the 1990s by these 2 professors in New Zealand who they were teaching statistics, and they wanted their students to have free software for doing statistics because, you know, software, books, all that stuff is expensive. So they created R, and they really just thought their students were going to be the only people that used it. But because R became this open source project that more people started contributing to around the world, and it became, and RStudio came out, and it became more popular. And now R is one of the top languages, computer languages used specifically in statistical computing and data science. It's used for other things too. You can get data from the web. You can get data from Twitter. You can analyze it. You can do text mining with R. You can do lots of stuff. You can use R Markdown and make web pages with it. So it's really versatile. But it's so popular now because all these people wrote these things called packages, which have all these functions that are useful for different things. The packages are basically just bringing in extra code that's more than just the base R package for different functions. This is a list of packages we're going to use. We're going to use ggplot2, which is the most popular visualization library in R. We're going to use Reader, which allows us to bring in CSV files. A couple of machine learning packages called Caret and Metrics. And then dplyr, which is really good for data manipulation when you want to filter and subset data, and you want to take all your empty rows and convert them or filter them out or whatever. dplyr is really good for that. So that's why we're installing these packages. And in order to do this, we have to actually run these lines of code. So we're going to highlight these lines from line 10 through line 14. And make sure it's all highlighted, and then you can click Run. And actually, I'm going to cancel because I have them all installed already, and then it would take a really long time and make me, I don't want to do that. Cancel. But for you, go ahead and click OK. You're going to run it. And what's going to happen is you're going to get all this red text. And it might take 5 minutes for everything to install. And some people, it depends on your setup. It might take a little longer. Some people, it might take 3 minutes. It's going to keep going and going. And don't worry, just kind of leave it alone. And so just kind of let it go. And when it's all done, you're going to see a little blue caret, a little blue arrow at the very end. But just kind of like let it go and don't worry about it and don't do anything else until it's done. So, all right, I'm going to leave that there. And as you're just going to kind of let it go, and I'm just going to talk a bit about machine learning for a few minutes, and then we'll go back to the hands-on activity. So you may have already heard about machine learning in various disciplines, and talking a little bit more about kind of in general what it is. And today we're going to go over what is the process of like creating a machine learning project and actually doing it. We're going to use R to do it, but you could use other languages. You could use Python. You could do it in SAS. There's lots of different ways you could do it. And also going to talk a little bit about why it might be useful, specifically in the field of business and finance. Sure, you've probably been following the market swings lately, ups and downs, and you know there's lots of factors there. But when I've been reading some articles about it, and when we have these days where the Dow might fall over 1,000 points, the next day it's up 500 points, and things like that, there's been a lot of writing about this, attributing those extreme swings to algorithmic trading. And of course, algorithmic trading is where you have computer code that's a computer program that's running and doing the buying and the selling and doing the investing, right? And so it's all based on logic and a set of rules. And algorithms are really just sets of rules that computers follow, right? It's just computer code. And so you're really taking the human element out of the kind of buying and selling stocks. And as a result, things can go really fast and really efficiently and follow this logic, but there can also be kind of surprising results or maybe even chaotic results that come of that. And so we're seeing that this algorithmic trading, because it's become so central and it's become so popular, that we are seeing some kind of interesting effects of that. And so these are, when we say algorithms, we're really talking about machine learning algorithms kind of at the heart of this. Another indicator that machine learning has become a hot topic in the business world is last year there was a 280-page report produced by data scientists at JP Morgan about, it's basically an investing guide for investors so that people can incorporate business machine learning strategies into their investing strategies, right? So it's basically explaining what machine learning is and what artificial intelligence is, which is kind of a subset of machine learning, and what big data is, like how companies can use lots of data to gain the edge over their competitors. And so the report is kind of an introduction to machine learning, but it's also a list of all the companies and all the firms that are using machine learning in their investing strategies. So if you have time, it might be worth checking out. But inside of the report, I have a quote here where the authors wrote, over the past year, the exponential increase of the amount and types of data available to investors prompted some to completely change their business strategy, while many are still paralyzed in the face of what is also called the fourth industrial revolution. So there's a sense now that because there's so much data out there available, it's become, some people have called it the new oil, data as the new oil, or data, it's that companies that can harness and analyze all the data that they have, it can be a very successful strategy. So again, just an example of how it's kind of become a hot topic. And also when you start seeing lots of online classes on something like online machine learning for business for trading or machine learning for finance, start seeing those, like Udacity.com has them, DataCamp has them. It's just an indicator that it's becoming a hot topic, or it has become a hot topic, and they're kind of trying to catch up. So what is machine learning? This is a basic definition from Arthur Samuel from 1959. So it's been around a long time, but giving computers the ability to learn without being explicitly programmed. So there still has to be some code, some programming involved, but you're not literally telling the computer every single scenario of what it might encounter. So an example of this is like a self-driving car, right? There's been Google and Tesla and lots of companies are trying, Uber, they're hiring data scientists, and it's really people with PhDs in artificial intelligence. They're hiring to try to create these cars. And you can imagine when you're in a car, there is no way to create a list of all of the scenarios that might happen in a car, all the driving conditions, all the possible things that could happen. There is no way to just make a list. It's almost like an infinite number of variables that are there. So you could not write a computer program that says, if this happens, then do this. If this happens, then do this. It's just impossible. And so they have to take a different strategy. So the cars have all these sensors, and there is computer code that's analyzing the data that's coming in, but it's also learning from the data in a different way. And so the car hasn't been explicitly programmed to do the X if Y happens and all of that, right? And so that's kind of an example of how it's a different strategy for getting computers to take in data around them, make decisions based on that, where the human hasn't explicitly told them what to do. So to break it down a little farther, it's machine learning is teaching a machine how to perform learning tasks. It's also teaching a machine how to identify trends in data, how to make predictions on data, how to recognize patterns that can easily be detected. So in some sense, it seems like it's all very positive, like it's something that would help humans learn more, do more, with data and all this stuff. Of course, there's some indication that especially when we talk about things like self-driving cars and when you have the algorithms that get so complicated, and this pertains to finance as well, when you have really complicated algorithms at work, humans may not actually be able to predict or explain what is happening, what the ultimate result is. And what may be happening, especially when computers are learning and like retooling their own algorithms, like humans might kind of not be able to explain the outcome, and it can lead to surprising outcomes. And so there's some kind of argument that as computers get more qualities, more abilities to intuit, to reason, that could be a scary thing, right? It's not always necessarily positive. So there is that. This article was published recently in the MIT Technology Review. There's another articles like how machine learning could actually increase social inequalities, and recent articles like that. So I encourage you to look at the articles about machine learning and the Technology Review to get a more comprehensive sense of issues related to it. You might have encountered machine learning online. There's so many, like Facebook, like any kind of like photo recognition stuff. There's also personal shoppers now. Has anybody kind of done shopping online where you've been recommended another product that other people bought, right? So it's on Amazon, it's everywhere. So now there are these bots, of course, that can speak and interact with people just like a person could. They can understand natural language. And so even though they're not robots in like a physical form rolling around, they are robots in the sense of being robots online. And they're really helping people kind of like, in this case, make shopping decisions. So they're kind of replacing a human who might serve as a personal shopper in that sense by just taking in data on a person. And here's a quick video I wanted to play for you of an example of that in investing. Oh, wait, hold on. Let me make sure I'm plugged into the audio real quick. Okay.
You've made some money. You want to invest. And you're wondering how to get started. Traditional financial advisors have high fees, high account minimums, and try to sell you products that benefit them, not you. But at Wealthfront, we know there's a better way to do it. We've taken the same modern portfolio theory that drives some of the most advanced financial advice. We're making it available to you. We use risk assessment algorithms to define the level of risk you are comfortable with. From there, build highly individualized plans. We show you your plan so you can see what you'll own before you commit. Then just fund your account, and we'll open an SIPC insured brokerage account for you. You can even transfer your IRA or 401k to invest in your plan. We continuously monitor your portfolio and periodically rebalance your account to keep your plan on track. A dashboard shows you everything you want to know about your investments. And what's more, you pay 75% lower fees than typical financial advisors. Wealthfront, the financial advisor for the new generation.
So what they're essentially saying is that this is robo-advising. It's basically just using algorithms to advise people on how to invest or doing the investing for them. And it's taking out the human financial advisor element. So part of this, you could call it fourth industrial revolution, part of like the changes in the economy now with machine learning and artificial intelligence is that it has the potential and it already has been replacing human labor in certain areas, right? So there is that also that fear that as we get more intelligent computers, there will be fewer people with actual jobs. So again, you can kind of see that there's different sides of the coin here, but here you can see an example of like using these algorithms and your data, we will give you investment strategies, right? Okay, so types of different machine learning tasks kind of fall into four basic categories. And the first is a classification category. And I'm going to go through examples of each of these. So just to kind of look through the list: classification, clustering, regression, association, rule discovery, and anomaly detection, where we get into like detecting credit card fraud and those kinds of things. And regression is the one we're going to focus on today in our hands-on activity. It's also kind of the most familiar one, I would say. But the process of doing machine learning is pretty much the same process across different types of tasks. And so even though we're going to be focusing on regression, the steps that we go through can be replicated doing other types of tasks. Classification would be a simple example would be to give the computer some data on images, like images of cats and dogs, and then give it a new image and say, is this a dog or a cat? That's a simple classification type of example where if you give once you train the algorithm to determine, okay, these characteristics seem to be dogs, these seem to be cats, and then you give it this image like this, and that you hope the algorithm might say, okay, it's 50% likely to be a cat, 50% likely to be a dog, that kind of thing. But what you'll ultimately get from running a machine learning model on this type of a classification is the computer will say it's 70% likely to be a dog, therefore it's a dog. Or it's 65% likely to be a cat, therefore it's a cat. So it basically gets statistical probabilities as your output, and then you have to kind of interpret those statistical answers from there. So it's using a lot of statistics to analyze information. All right, so clustering algorithm would be the next type of algorithm that we see in machine learning tasks. And so how many different clusters of data do you see from this graph here? I know it's kind of washed out, but how many groups or clusters would you say there are in this particular data set? 4? Okay. So we've got a clear one here, and then you might have one here and one here. And so this is flower data on flower petal height and width. It's one of those data sets that's like often freely available. And so depending on how the algorithm is trained, the computer might return, different 3, 4 clusters, right? In this case, it saw 3 clusters. And so there's that middle cluster that computationally, using a k-means algorithm, it saw 3. You can tweak the algorithm to get more clusters also. So again, it's kind of like a science and kind of an art when it comes to analyzing and interpreting data. And it may be the case that there's actually 4 clusters. So I'm not saying that you're wrong. It's just this particular algorithm, given how it was trained, sees only 3. And regression deals with the relationship between variables. So given a couple of variables, and you might have more than 2, but given 2 variables, what's their relationship? Is there a linear relationship between these 2? So there's different types of regression, and today we're going to be working with linear regression. But it's often like for predictive purposes. So today we're going to look at employee salaries and whether or not that influences job satisfaction as our first example. And that's looking at those 2 variables and how they relate. And so another example would be association rule mining. So looking to see if there's associations or patterns in the data that we would maybe not otherwise find. So there's a study that's kind of famous about purchases of different products and how there seems to be a correlation between purchases of diapers and purchases of beer. So is there really a relationship there? And this is one of those examples of like this a famous study. Like it seems like people tend to buy diapers and beer together. Like why is that, right? And if you have kids, that may make more sense. I don't know. But it ultimately kind of came down to, okay, on a Friday night, and I think it was kind of time related. Like it happened more on Fridays. On a Friday night, it was often, again, I'm not trying to generalize, but this particular study found there were dads going out and buying diapers and also tended to buy beer. So the idea, if you're the store, like if you're a supermarket or convenience store, you might put the diaper aisle right next to the beer aisle, or you might put them on the same aisle, but I don't know. But you at least have them close by so that it's easier for people to get what they want, or you suggest in ways, I guess. Or in this case, you might put milk and bread on the same aisle or close by each other because of that as well. People tend to buy those two things together. And then, of course, in the deviation detection example, the algorithm is looking for the outliers. So in this data set, we have locations, we have DH Hill, we have Durham, we have home, whatever home is, Hunt Library. These locations are all like very close by. And then you have, in the data set, we had California show up and Paris, right? And so if this was credit card location purchase data, this might be a flag for the credit card company or the bank to say, you know, your card was used in these other locations. So that's another common example that we see when it comes to machine learning tasks. That's happened to me before. Has it happened to you? I forgot to let them know I was traveling and then my card got canceled. So, all right. So quickly, we'll go over the process for doing a machine learning project, which we're gonna then actually do using code. The first thing is like really obvious, but it's important to state, is that you're gonna get some data. You wanna get a lot of data usually. It might be in the form of files, it might be data you get from the web, it might be images or audio recordings. But you wanna get that data into a cleaned state, and you wanna get it into a software program. So we're gonna be using R today, but Python is also really good for machine learning. And there's other kinds of software that you can use as well. Cleaning data often takes, like their pre-processing data, which is more than just cleaning, it's kind of getting it structured in the right way, often takes a lot of time, maybe even the most time. And this data on the left is what we would consider messy data. It needs to be dealt with. Does it look really messy if you look at it? But you'll see that if you look at this data, which is actually considered clean or tidy, there's some different characteristics here. The ideal, and this is for like if you're creating any kinds of graphs or charts, it doesn't have to just be machine learning. Let's say you wanted to create a chart and you have an Excel file, or you're using Tableau or something like that. The ideal shape for data and the ideal structure is that you have one variable per column. So you have name, treatment, and then result. So that if you have in your data, like if you have lots of variables, each of those variables will just be one column. There won't be multiple columns. You see this when you see like World Bank data or something where you have each column like a year, 1991, 1992, all that. Well, that's actually a problem because the variable is year. You really want to have one column with all the years going down. It's easier to manipulate the data that way and to visualize it. So in this case, we have treatment A and treatment B as two separate columns, when in fact treatment should be just one column and the types of treatment listed like this. So that's just to think about like how certain data structures are bad for certain types of analysis and certain types of visualization. Of course, you want to make sure there aren't any like errors or misspellings in the data. Checking data quality is really important. That's kind of an obvious point. More interestingly, though, when you get into doing machine learning and you're training your machine learning model, you realize that some variables matter more than others. This is an example of the Titanic data set, and the data set is about individuals that were on the Titanic when it sank and basically who lived and died. So who lived or died. And these are, this particular visualization shows the variables that had more weight or mattered more in terms of who lived or died, kind of listed in greatest importance to least important. And the greatest important one was the title of the person, Mr. or Mrs., Miss, those titles were listed in the data set. So what do you think, Mr. or Mrs., who was more likely to survive? Mrs., right. And the fare that they paid, so the amount of money that they paid also had much more weight in determining whether they lived or died, which indicates social class status, right? If they paid more money, they were, you know, they had a certain cabin type, it was often because they were wealthier. So, and then these, where they embarked from and their family sizes were less important in terms of whether they lived or died. So this is kind of like what you're trying to do is like when you're working with lots of different variables and you may not know which ones are most important. Part of the process is determining, using statistics and that kind of thing, which ones are most important and eliminating the other ones when you're training your model. So in this case, this is part of the data. We have the names of the individuals and their titles are included in the same column. It would probably be better to pull out their titles into a separate column and have title be a variable in the data, which would allow us to do more. We would be able to train our model better and get a better outcome. Since the title is so important, we want to have it in its own column. So I've talked a lot about models, so I haven't really defined what that means yet. So a machine learning model has two things that it needs. One is it needs data. It's made out of data, and it's made out of an algorithm. And the algorithm is just a list of instructions a computer will follow. And so in a machine learning task, there's lots of different kinds of machine learning algorithms, and this is like by no means an extensive list. We're going to be working with linear regression, but there's also clustering algorithms. There's the ones that we're looking at with the chatbots and with the self-driving cars. Those are the neural network algorithms, which try to replicate the abstract and kind of complicated processes of the human brain and how we think. So some of these are more complicated than others. But it's important to kind of just know that there's lots of different algorithms out there. And so again, a model is just training data and an algorithm. With training data, you want to have like a lot of data, and the data is historical, meaning it's events that have already happened. And that could include audio records of a person's voice, stock market data over time. It could be Amazon.com purchase history. It could be any number of things, any kind of media, any kind of text data, whatever it is that you want to do. So it's not really limited in terms of data type, but you just want to have a lot of it. And so part of the process is a model has to be trained. So this is getting to where you're trying to teach a computer how to learn. You give the computer some training data, and the computer, the training data is like a random sample of your entire data set. And you feed that training data into the algorithm, and it will help the computer learn. So when you give it new data, it will perform the task that you want it to perform, hopefully. So the training data is, again, the random sample of the larger data set. And you actually divide the training data into two sets. The training set, which is a smaller subset, and the test. So when you have training data, you don't use all of it for training. You actually use a lot of it for training and then some of it for testing, because you have to have some data for testing so you can test how accurate the model was. So in this case, you have these kind of reddish orange dots and you have the blue dots, right? And you're going to train the model, and you're going to give it these two different categories of dots and tell it what characteristics it's looking for. And then you give it a new dot, and it has to sort into one of those two types. And that's your model is basically your prediction function. It's taking the data in and it's doing this task. And then the second to last step, of course, is testing your model. And then based on what tests that you get, which are often statistical tests, but you can also create visual tests like charts and graphs to see how visually accurate something was. But then you're going to need statistics to analyze it. And then once you do that, you might find you need to go back and tweak your model a bit. It's not quite where you want it, and then improve it and all of that. So it's constantly this kind of what we call iterative or cyclical process of creating the model, giving it data, going back, and tweaking the model and that sort of thing. You may need a new algorithm, so you may swap out algorithms and that sort of thing. But today what we're going to do is we're going to do 2 different exercises. And the first one is going to be try to predict job satisfaction or happiness based on salary. And we're just going to use a little bit of data for that. And we're going to get used to the process and the functions that we're going to use in R. And the second exercise we're going to do is looking at some market return data, financial data, and we're going to look at predicting a normal return based on a ranking determined by dividends to asset ratio. So that'll be where we have a data set that has over 100,000 rows, and then we have a little bit more data to work with. So to do this, we'll go ahead and kind of get back into RStudio. If you want to go ahead and bring up RStudio, this is going to be the hands-on part of the workshop. And I'm going to clear out my view here. Okay. So hopefully everybody is seeing, once your packages were installed, you should see this little blue caret at the bottom of your console. The console is the area where you're going to get messages about your code once it's run. It'll give you output and it'll give you like errors and debugging type messages. So when we run pieces of the code, you'll see the output here often. After installing packages, which you only really need to do once in R, in every R session, you always have to load the packages that you want to use into your session. So after you use R a lot, you've installed lots of different packages. And at the beginning of your R session, you're just going to load the ones in that you need. So if you go ahead and highlight lines 17 through 21, this is just loading those packages we installed into the session, and click Run. In your console, it should just print out the same code. And if it's blue, you know that it worked. If you get red text that says error, then you know there was an error. So if anybody's getting an error, if you could just raise your hand and Heidi can come around to help. Otherwise, if everything is blue, that means it loaded everything properly. Yeah. How do you clear your console? On a Mac, or usually I think it's actually both Mac and PC, you do Control and L. So Control L will clear it. Did that work for you? Okay. All right. So we've loaded the libraries we're going to need, and now we're going to go down and scroll down a little bit to exercise 1. So we're going to do our job happiness prediction exercise. And the first thing that we have is data on an employee's earnings. So these are all different employees, and each of these, this is like thousands of dollars per year. So 120,000, 100,000, all of that. So we're going to go ahead, and you don't have to actually highlight the whole row. You can just put your cursor on the row and then click Run if you want to. And that will run it properly. There's also a shortcut. You can do Control Enter on a PC, or you can do Command Enter on a Mac, and that's another shortcut to running the code. The second thing you're going to want to do is run line 30. This is the satisfaction rating in terms of percentages. So is an employee 70% satisfied? Are they 30%, et cetera, right? So we're going to go ahead and run that line. And that's going to, if you look at the top right-hand corner, every variable that we create, we're going to see a summary of that, or we're going to see information about that variable in our top right-hand window, which is called our global environment section. So that's just a place where we can kind of double check that the variable was created correctly. And so right now we just have 2 lists of numbers, and what we want to do is actually bring them together as a table. So we want to have columns and rows. So line 32 does that. It creates our data table, which in R is called the data frame. And it uses a data.frame function, and it brings together those 2 lists, also known as vectors, of earnings and satisfaction rating. So you'll just run line 32, and you'll see the data frame pop up here on your top right. If you click on that little, if you see I'm hovering over this little icon, it looks like a square. It's like a tabular data set. If you click on that, it will pop up a new tab where you can visually look at the data that you just created. So we've only got 15 observations or rows in this data set. So it's pretty small, but it's good for practice. So in line 34, the next thing we're going to do is we're going to just create a scatter plot of the data, and we're going to look at X and Y. You know, we're going to look at X as our earnings, and y is going to be our satisfaction rating. And this uses ggplot. So we're going to click run, and it's going to pop up on the lower right. So we'll get a graph pop up. And we also included into this line of ggplot code here in line 34. I asked it to plot points at the x and y coordinates. That's the geom_point function. And then geom_smooth is it's going to be drawing a linear fit line. So we've got our fit line here. And it does look like there's a linear relationship to this fake data, basically, right? So, so we haven't done any machine learning yet, but we've gotten our data prepared and we've kind of explored it visually. And our next step is doing starting the process of creating a machine learning model. Line 38, set.seed. So remember how when we create a model, we have to get a random sample of our data set as our training data? Well, because we're selecting a random sample, we need to have a seed where we start. Because in case somebody runs this code later, we want them to get the same results. So this is for data. This is like for reproducibility. And you have to set a seed when you're doing a random sample model. So we did that already in line 38. And we can pick whatever number we want. As long as they have the same number, then it'll work fine. Line 40 creates a data partition. So it's going to take that random sample, and then it's going to divide it up into our training and our test data. And this comes from the caret package. That's the create data partition function. And we're going to it's going to partition the data. It's going to take in the y variable as the satisfaction rating. And it's going to partition the data as 60% training and 40% test. And all it does, this is really just getting a random sample. That's all it's really doing, is getting a sample. So we're going to run that. And then to create our tests and training sets, we're going to need to actually also run lines 42 and 44.
Or did you run line 38?
Did I? I don't know. I might not have. Thank you. I'm going to go ahead and run that. Okay. And then, oops. So go ahead and run through lines 44. And you'll see in your top right, once you do that, then it's created a test set and a training set. And you can see how many numbers of observations or rows are in those two. So it's divided it up. We have more data in our training than our tests. And that's good. That's what we wanted. In line 46, we can just see the head. The head function gives us this.
Sorry.
Yes.
You skipped the line 40?
No, I should have done that too. I went back and reran it. So we definitely want to make sure, and I might have made a mistake. You definitely want to make sure to run lines 38 through line 44.
Okay, could you please repeat what does it mean the 100 inside the parentheses of the seed, set seed?
Yeah, so that's just a starting number. So the seed number, it could be any number. It's useful for when you do any kind of random sampling of data and you're picking out like random rows of the data. The reason why we set the seed is for the next person who reruns the experiment to start with the same seed. It sets a beginning point for the random sampling. So if they don't use a seed or they have a different number, they're going to get a different random sample. And we want them to get to the same sample. And so that's all it's for, is for reproducibility. Yeah. Okay. So let's go ahead and look at the training data by running line 46. And we can see just the first 6 rows of it. And then we're going to go ahead and look at the summary of that data. It's a statistical summary by clicking run. And it'll show us the 2 variables that we have in the data set, and then the min and the max, the kind of range, statistical range of that data. So this is a really good place to see if there's any outliers or any issues. And the dim functions in line 50 and 52, which we can go ahead and run. Those just tell us the dimensions of those 2 data sets, which we already know that this is really small data. But let's imagine you had 1 million rows. The dim functions are really helpful for knowing how many observations are in each of your training and test sets. So it's helpful to kind of quickly look at those. Step 3, we're going to train our model. So we're going to do a regression model. we're going to call the model reg underscore model, and we're going to use the LM function, a linear model function, to create that. And we're going to pass it in to the function our satisfaction rating column of data, and then that's going to be basically our Y column. It's also called your response variable. We're also going in the X position, we're going to pass in the earnings. So the earnings is like the input, and the thing we're predicting is the Y, or the response variable, which is the satisfaction rating. And we're telling it that we want to train the model on our training set that we created. Let's go ahead and just run that really quickly. And that creates our model. And then we can run line 58, the summary of reg model, to see what the model coefficients are and get some information about our model. Because our model really isn't like a visual thing. It's really just it's a statistical thing. So this summary allows us to see some important information. So in a linear model, we have basically the formula is y equals ax plus b. Pretty similar, like we've learned this kind of in middle and high school. It's the algebra type of formula, so it's pretty easy algorithm. And our coefficients are the b coefficient is our intercept, is in this case 34, and our a coefficient is going to be 0.2095. So we see it's a positive. These coefficients are positive, and so our slope is going to go upward. We can also see some other important statistics here, and the one thing I'm going to focus on is the p-value. And the p-value here is below 0.05, so it's statistically significant. This relationship between these two variables is significant. So we can proceed knowing that we've kind of passed that p-value test. And so let's go ahead and move down to 63. This is the coefficient function is just another way to find our coefficients that our model created, and it just prints those out rather than all the other data that we printed out. Now that we've created our model, we are going to, and we created our model using the LM function, and we passed in, we used data to train the model. It doesn't seem like we did, but we used data from the training set to train it. And now what we're going to do is pass in data from the test set to test it. And how we do that is we're going to create a predict satisfaction function. And in the carrot package, there's actually just one line of code that you have to write. It's like there's a predict function, but I wanted to write it out in this way so you could see the math that's involved in what's actually in the function. And so what we're doing here in R is we're creating our own function, and we're setting our b coefficient equal to the first coefficient in our reg model. And our a coefficient is the second coefficient in our reg model, because they're just listed one right after the other. And then we're returning a times x plus b, and that's going to be our result. So now what we're going to do is pass in our test data here into this x position up here. So we're going to pass our data into here, and it's going to basically go through here, and we're going to multiply whatever the person earns, like the first person earns, we're going to pass that in, and it's going to multiply by the coefficients, and it's going to spit out the result. So we can do that in line 74 by just running 74. Oh, I'm sorry. I forgot to say that we have to run line 66 through 72 to create the function. And to create our prediction where we're passing in the earnings data from the test set, we'll do in line 74. So you see that $sign that's inside the parentheses? What it's doing is it's saying, okay, I want you to use data from the test set, and I want you to use the column that's earnings, the earnings variable data, and pass that data into the function. Just click run. And we're going to go ahead and we just have a list of predicted values. We're going to turn that into a data frame in line 76. And it's not really useful until we can actually see it and we can compare the test data to our predicted data. So in line 80, what we're going to do is print that out. Just click run, and it's going to print out, okay, this was the test value is like the actual satisfaction rating that the person had. And we predicted that they were going to have, our prediction is in the other column. So we predicted this person was going to have a 61% satisfaction rating based on our algorithm. They actually had 75%. So we're a little bit off. In the second example, we predicted 65 and they actually were 60% satisfied. It's actually okay that we're a little bit off. If we were exactly right every time, that would be called overfitting the data. And that can actually be kind of bad when it comes to creating a good machine learning model. So you do want to kind of get it close, but you don't want it to be exactly right. Because when you pass in new data, if the model is overfitted, it actually will do worse in many cases with new data. So that's that. And then if we want to find out the standard deviation of how our prediction deviated from the actual data, we can run a function called RMSC, and that's the root mean standard error. And that's just basically giving an overall statistic of saying how much the predicted values were deviated from the actual values. And you can run that and see it pop up in the console here that we get a number of like 9.78. So it's the root mean standard error is going to be different depending on the data that you have. There's no like, we're not trying to get to a particular number here. So to interpret that, we like to look at the range of the data overall and compare that standard deviation with the range of the data. So the range of the data is in line 86. We see that the minimum value is person with 60%. The minimum value from our test set is a person with 60% satisfied, and the maximum value is 85%. So the range is like 25 percentage points. And a standard deviation of 9.78 might be a little high given our particular range. So we might want to try to lower that by tweaking our model in the future. We could maybe add some more terms variables to it, some more X variables. We could maybe pick a different algorithm, or we might be satisfied with what we have. So the task of a data scientist is to really tweak the models to get the outcome that best fits new data. And like, it's a process. But that's the general process of how you would do it. Any questions before we move on to the bigger data set? Okay. All right, so we'll move on to exercise 2. And this is doing pretty much the same stuff that we did in this previous shorter exercise, just using a bigger data set and different variables, but it's kind of the same thing. So you'll see it's the same process going through. In line 92, we have to read in our data. So we're using a read_CSV function, and that's from the reader package in R. But go ahead and run line 92. And you'll see we're saving that spreadsheet to a variable called data. So go ahead, and if you'll click on this little icon over here beside data up in your environment section, you'll see the variables, you'll see what the data looks like. And so I can run through it really quickly here. Key is just a company key. So this is, each row is a company. The date is the year, the day, and the month. So the data goes from 1997 to 2016. The historical ID is just an ID variable that we don't need. We've got the market return, dividends to asset ratios, the ranking based on dividends to asset ratios, raw return, an abnormal return, and the year. So we're going to be focusing on the abnormal return to see if there's any relationship between that and the company's ranking based on its dividends to asset ratio. So again, we're just going to be doing a linear regression to see if that kind of algorithm fits this data. When we look at the data in line 94, we'll see that R thinks that all of these variables, the market return, the assets ratio, the abnormal return, R thinks these are all string variables. Like, it sees this as just string or text data. It doesn't see them as numbers, because the missing values were periods in the original data set. It saw those as strings, so it made the whole column string variable. So that's actually bad for us because we want to do statistical analysis. We're going to have to convert that to number values. And lines 99 through 102 we'll just highlight that and run those. These are taking each of those variables and turning them into numeric variables. So I'm just going to run that. And you're going to get a warning. And where it's all those little all those little periods, it changed this NA values. So that's okay. That's fine. And then now we're going to do some graphing. And we're going to create a scatter plot where we're going to be looking at rank, the company's rank on the x-axis and their abnormal return on the y. So abnormal return would be how different the actual return was from the expected return for that company for that year in terms of their return. So let's go ahead and do run, and it's going to take a minute longer. Last time I did this, it took me like an extra long time to get it to pop up, and it might be because I'm projecting for some reason, but hopefully your graph will pop up pretty quickly, and you'll see that there's a lot of data here. In the function I used, so in the function on line 107, you'll see the function geom_jitter. I'm jittering the data because otherwise the data would all be like overlapping itself, and you wouldn't see very much. But when you add a little jitter to the x variable and it kind of plots the x variables kind of like beside each other, it's kind of adding a little bit of noise. You'll then see that there's a lot more data there than you otherwise would have. So if you want to take the geom jitter out and replot it, you'll see that there's just a few points on the graph because everything's been written over itself. I'm also setting the alpha variable here because that's giving the dots a little bit more opacity so you can see what's behind them. So you can see more overlapping. And then I'm adding a linear fit line and some labeling. It's taken me a bit longer. Did everybody else get the graph to pop up? Okay, great. So you can kind of see that the linear fit line looks like it's kind of at 0, right? It really doesn't look like it has much of a slope to it. And so because our brains can't really see it, so part of this is just to see if there is any type of slope at all to this line. The next thing we're going to do is to plot the median values of abnormal return by rank. So we're going to aggregate all 100,000 rows into just 5 data points. So let's go ahead and run the first line 110 is just to create the median. It's like by group processing. Basically, we're creating the median for abnormal return by rank. We're going to run that. And then our line 112 is plotting rank and the median abnormal return. So when we run that, you should see a much simpler graph. It popped up for me because it's a lot less data. You should see this graph. It looks like there's some linear relationship of rank and abnormal return. But this is like really, really aggregated. And also you kind of remember that this data goes from 97 to 2016. So what if we broke it out by year? In our next graph, we'll break it out by year. So every year will get its own graph. We're using some functions from the tidyr package in R to do that. We're using the group by function and the filter function. We're going to filter out all the missing data from abnormal return. And then we're going to, in our ggplot function, we're going to use a little bit of one little tiny function called facet wrap to break all the plots into subplots by year. So we can go ahead and run all of that code from line 115 to 120. And then it will give us, hopefully, a nice kind of breakout by year. And we can see some years look a little bit more kind of upward slopes, and some years look a little bit more downward, and some look flatter. And again, it's a lot of data aggregated, but it helps. These kinds of plots can help us to analyze the data more. So once we've done our kind of visual analysis, we can then get into the machine learning part of this. We're going to create a regression model using all of the data that we started with. So not the median data, but all of the data. And that's going to be in lines 125 and 126. So we're going to create the only thing we have to do is filter out the null values for the abnormal return variable, because otherwise it wouldn't do it properly. So we do have to take those out, but everything else is going to be in there. So let's go ahead and run that line 125 and 126. And we can see how much data that is by looking up at the information in our global environment field. We'll see the data for model data set is 93,002 rows. So that's still a lot of data, and it's a good amount of data for doing machine learning. So in line 132, we'll scroll down. We're going to do a set seed again. I'm going to run that. Again, I've picked 100 as my kind of arbitrary number for that. Then we're going to create a data partition again. We're just going to use abnormal return as our variable for that. And this time, we're going to do a little differently than the previous exercise. We're going to choose 75% of this data is going to be our training set. And then 25% will be the test set. So we're going to use a little bit more data, a bigger percentage of the data this time. Kind of messed that up. I got to rerun it. Okay, and then we can go ahead and highlight lines 136 and 138, which create the training and test. And we can look at the first few rows of our training data in line 140. Okay, so we're good. We can see that abnormal return is a double. This is a numeric data type. So that looks good. So far, everything looks good. Line 142, we're going to do a statistical summary on our training data. And here, we can look at all the variables in our training data. Of course, we're not going to use all of these, but we can focus on abnormal return and see that the range of the data is pretty big. We have the minimum value is -1.43, and the maximum value is 58.425. So it's a pretty big range. And this is a good time to find outliers and see if there's any problems in the data. You can use the statistical summary for that. And so we're going to run the dimension functions on training and test just to see what the dimensions of those data sets are. And so we find out that our training set has 69,753 rows, and our test set has 23,249 rows, and both have 9 variables. So just to make sure that the data partition was done correctly, it looks like it was. And so now we want to train our regression model. So we're going to, again, call it reg model. We're going to use the linear model function, and our response variable, or our y, is going to be abnormal return. And our x is going to be rank. And we're going to use the data for model data set. So we're just going to go ahead and run that. And we're going to look at the summary of our model, which is going to give us our coefficients and our p-value. Our b coefficient, or our y-intercept, is going to be 0.0969. And our ranking coefficient, our a coefficient, will be -0.0130. So we do, using all of the data, it does seem like there's a negative, potentially negative slope to this data. And then the p-value is really, really low, basically 0, 5.265 times e to the -15. So again, it's really, really tiny. So it does seem to be like there's a relationship between the two here. So we're going to look at our model coefficients again, just by running the coefficient function. We don't need to do that. Just to know that that's possible. And then we're going to create a prediction function that's just exactly like the predict happiness function, just using a different data set. We're going to run that. And then now what we're going to do is feed into our prediction function our test data. And what we want to do is give it a rank. So given a company's ranking, what should be its abnormal return? So we're going to feed in some test rankings, and then we're going to spit out our predictions for abnormal return for the data. So you can go ahead and run 168 and 170. And then 173 is going to print our test column right beside our prediction column, so we can compare how well we did. And there's a lot more data here. So to kind of look at it all, you want to scroll up a bit. What you might notice is our predictions were all positive, and a lot of these values in the actual data were negative. And you can kind of compare, like, here's negative 0.8, whereas we predicted a positive 0.0969. So there seems to be some of these that are pretty far off the actual values. And it may actually be pretty hard to predict a company's yearly returns or predict a company's abnormal returns just based on their ranking, right? So it may be the case that a simple linear model like the one we have might be a little too simple for doing this work, or we might need to add some variables to it or adjust it. But in order to figure whether that's true or not, we can do a few things. First, we can check the accuracy of our model visually by just plotting it and seeing what it looks like. So looking at our test data, we can go ahead and run line 177. Of course, I'm not sure mine will pop up or not. So it looks like we have, if I make this a little bit bigger, the linear model is really close to 0, and it's really hard to see the slope, but we see there's a lot of like noise and a lot of variation in terms of this abnormal return variable, and that there are some outliers. So whereas like our median data was like very clearly linear, kind of like there was a linear relationship, this is a little bit harder, even though there seems to be, given our p-value, there seems to be a relationship, it's still kind of, there's still a lot more outliers, right? And so step 14, we can use statistics. We can, again, look at the root mean standard error and see what that value is. And it's just the standard deviation between our predicted versus the actual values that were in our test set. And we get 0.9296. And we can go back and look at the range of the test data to kind of see where the standard deviation falls there. And the standard deviation is like 0.929, and our range goes from -1 up to 53. But the 0.929 falls pretty high. You know, it's not anywhere near the median, and it's ideally we would want to get it closer to 0. So it may be the case that the model does need some tweaking, depending on, you know, what kind of accuracy we're looking for. And it may also be that a different algorithm, such as random forests, which can do prediction like this, but takes in multiple variables and which variables are more important than others, something like that might also be applicable to this kind of data and might even be more accurate. And so trying out different algorithms also is helpful. Any questions? Yeah. It depends on how many. So you're using data for model in your model, right? You're using the same code. Let's see. I wonder why that's the case. If we're using the same script and the same seed, and where I have commented it out up here, you didn't uncomment this, did you? You didn't run that. Okay. It might be an issue with. I wonder why. It must have removed. I have to go back and look. I don't know why, because I think we're using the same data. Because this is the data that I downloaded last night. So for some reason, it's left out the 53 or the 58, and I don't know why. It's a great question. Oh, yeah. Sorry, that's right. But if you use the same seed, it should have given you the same numbers in your sample data set. So I'm wondering if that, ideally, So yeah, that would make sense that for some reason that when it was doing my random sample, it didn't select 58 as part of the test set. So we could go back and compare our test data sets to see if they're exactly the same, but of course, they're so big. Well, we could look at our summaries and yeah, it looks like there's something that happened with the sampling. I'm not sure why, since we set the same seed, but I'll have to go back and look at it. That's a great question. Other questions? Did you get a different root mean standard error? You got a different one? It's possible that, yeah, I don't know. Maybe I remember when I was running this code, I first forgot to set the seed. Somebody pointed out over here that I maybe forgot to set the seed when I started to run it, and maybe that's what happened. I don't know. And then I went back and redid it, but I'm not sure for some reason. The sample might have, because I did it out of order, I might have like messed up the steps or something like that. But if everybody else got 58 and everybody else got the same root mean standard error, then it must have been something that I did out of order here. So just ignore what I did. But it seems like you guys had the right conclusion, the right answer. Any other questions? All right, well, great. Thanks for having us here. And if you're interested in doing more with R, and maybe you've already been in other classes, or maybe you've already worked with R some, but if you're interested in doing more with R, we have workshops at the libraries on data visualization with R, getting started with R, and we're going to be doing some data cleaning with R too. So just keep an eye on those. Thanks a lot.
Thank you. Very pleased to have Alvin and Heidi come here and so thank you very much.
Thank you.
And